Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so it's a pleasure to have Marina Blanton with us today. Marina's from the University of Notre Dame, and she's done a lot of work in security and cryptography on key management, biometrics, and cloud storage. And I guess today she'll be speaking about biometrics.
All right, good afternoon, everyone. I appreciate the opportunity to visit Microsoft Research and be speaking here today. So as Sani said, this work, this talk that I'll be presenting today deals with secure computation of biometric operations and secure outsourcing of the same computation as well. And it combines a couple of results that they have, and perhaps it might be ambitious, but this is a good audience to be talking to. So I'd like to cover a couple of different topics that I have. So as I said, I'll be talking about secure computation of biometric operations, biometric comparisons that actually involves a two-party computation. Then I'll proceed with secure outsourcing of the same type of computation to one server and to multiple servers. And the last part that I would like to mention is on verification of the result that comes back from outsourced computation. And so most of it deals that I'm going to be talking about iris codes, comparing two iris codes, but the last part that deals with the verification is applicable to different types of biometrics, okay? But most of it is for iris codes. Okay, so here, let's start. So in general, when we talk about biometric data, we understand that it's sensitive, right? And I like a lot of different types of information that can be used. This is something that we can just invalidate and get new biometric, right? This is sensitive, and also it's worse because it can be changed to something that if it's compromised, we have limited options in this case. So for that reason, we want to protect this information when it's used throughout the computation. And there is a lot of different scenarios when protection might be required. And in particular, I would like to see we have, for instance, two databases, right? And by law or other regulations, I'm actually not allowed to see that database, but it's actually, for us, advantageous to compute whether there is some biometric that appears on both of them, right? It also could be that my computation is so large in scope that I can't do it on one machine or the computers that I have available, and I have to, outsource it. And the same thing happens here, that the data is sensitive enough that I would like to be able to protect it. And even if it's not for outsourcing reasons, if something happens on machines that I own, but they're not trustworthy in some way, and we would like to be able to protect that information from break-ins or malware or some other malicious behavior, you can apply these techniques as well. Okay, and the main problem with biometric data is it's noisy, right? When you take a sample, you take another one, two biometrics are going to be different, two samples that correspond to the same person or related biometrics. And often in cryptography, when you apply techniques such as hash functions, for example, right, by design, they'll diffuse the differences so much so that by looking at two outputs of very closely related inputs, you can't tell if they're related or not. But in this case, we actually want the opposite, right? We want related biometrics to remain similar, and so we have to use some other techniques. Okay. All right. Let's see. So there are a couple of different scenarios that I'll be referring to throughout this talk, and the first deals with sort of secure multi-party computation. And I'll be talking about two-party computation, and it could be that, say, one person has a database, maybe the government, right? And there's private agency that's processing and investigating some of the people. They have their samples, but they're actually not allowed to get just access to the federal database. And so in this case, they would like to see if that biometric appears on a suspect list somewhere, but they can access the database. They also not necessarily willing to give all of the data that they have available. So in this case, we would like to see we would like to answer the question, is my biometric appears on a database of that a different party has, right? So we basically would like to compare our biometric with each biometric that's stored in the database and say, yes, there's a match or there's no match, right? There's no relationship between the two. And the second scenario that actually motivates this work is outsourcing, but this is something that happens close to us, because in our department we have a large, strong biometric group, and basically what they do, they collect a lot of biometrics from students and other people who are actually willing to help them with this collection. And the database is actually very large. Right now it's about 100,000 different biometrics that they store. And when they test a new recognition algorithm, what happens, they actually take each biometric in their database and compare it to every other. Okay, so the computation is very large in scope. They can't use it from one machine. They run it out of memory. They don't have enough computing power, so they send it to a grid. And right now it happens all in-house, but if we could have techniques where you protect the data as it's used throughout the computation, that you can use external resources basically anywhere when it's available. So this is two different scenarios that sort of relevant to secure computation over biometric data. So let's look at a specific scenario, right? So what I have here is, from now on, I'll be looking more at iris codes, right? So basically, this is the pattern that they can extract, take picture of an eye and extract pattern that's unique to a lot of people. And actually, it has a lot of information, much more information that you can get from fingerprints or some other types of biometrics like faces or palm prints. Mm-hmm.
By information, you mean it's more likely to be?
There's more entropy, right? So they say that there is 250 degrees of freedom in the basically data that they extract. So basically 250 bits that you can get, and normally it's you can't get that much from fingerprints or something else. Okay, so we have two parties, Alice and Bob, right? So Alice will have a database of images, so it could be large, and we will say this is D, and Bob has a biometric image, and Bob would like to know whether this image appears on the database or not, if there is another one that's related, okay? So, after taking a picture, so all of them just take a picture and extract features. And in this case, you can actually represent each iris code as a binary string, okay, of certain length. And this is independent of the databases or anything. You can do this for any biometric. And so in this case, when they would engage in the computation, right? So for each biometric in the database, Bob will engage in a computation with Alice, and then they compare Bob's biometric with the first biometric in the database, second, etc. Okay, and they actually learn for each computation, they learn yes, no. Basically, yes, they're related, or no, they're far enough that they're not related. And so you can specify who learns the bit. In our case, we say, for instance, Bob learns the bit for each computation, and then normally there will be one match or there will be no matches. Okay, so they'll be able to tell if that person appeared in the database or not. Okay. So let's take a closer look at how two iris codes are compared. As I said, each iris code is represented as a binary string. In general, to compare, to compute a distance between two binary codes, you would compute a Hamming distance, right? You have one code, another one, and you count how many bits are different, okay? And this will be the distance. So the more bits are different, the larger the distance between them is, and we basically want to see if the distance between two iris codes is within a certain threshold, and then are considered to be related. Okay, but it gets a little bit more complicated because with these codes, what happens is when you extract features, you have this binary string but there's quantization involved in producing those bits. And some of them are unreliable, meaning that we had a hard time deciding whether we should set it to 0 or 1. And for that reason, there is a second binary string of exactly the same length that says, that's called the mask, right? And it says that certain bits should be marked as unreliable, and we don't want to use them in the computation. Okay, have one string that's the code itself, and then another one that says, if the mask bit is set to 1, say we're going to use this bit of the iris code in the computation. If it's set to 0, we'll say ignore it. This is not reliable. We can't make good decision based on those bits. Okay, so for that reason, the distance between two iris codes, in this case I'll say X and Y, will be a little bit more complicated. Okay, normally this is actually the notation that the people who do biometric recognition use, right? But this is what is more intuitive to us. This is what I would do. So here, this is the Hamming distance between two basically strings, and we also from that string, where you do XOR, right? So some bits will be different. Some bits, where the bits are different, you're going to have 1. Where the bits are the same, you're going to have 0. And basically, you want to count how many 1s you got. Okay, but this means that in addition to computing this, you also want to make sure that only the bits that are set to 1 in both masks will be used. Okay, so this basically says for each bit of the iris code, I first do XOR, but I'll add it to the distance only if the same bit is set to 1 in both of the masks. Okay, so this is actually the distance itself, but then you also want to scale it to be, say now we're not using all of the bits of the iris codes, right? And I want to make sure that this value is comparable, but actually depends on how many bits we've used, right? So we'll also divide it in some way normalize it by dividing it for the number of bits that are reliable in both of the iris codes, okay? So we compute this Hamming distance only using the bits that are reliable and divided by the number of the reliable bits in both, okay? So this distance will be between 0 and 1.
This looks equivalent to a ternary system where a bit is +1 or -1, or God only knows which is 0.
So you mean for the iris code itself?
Yeah. You have +1 bits, -1 bits, which are hard, and 0 bits, which mean you have no idea. And then it just becomes a dot product.
Yeah, so in this case, they use only, there's no -1, right? Okay. And so after you've computed the distance in the way that I specified, we want to compare it to a certain threshold, right? This T is fixed. It could be, 25% or, 30%, and then I consider it related. And so what we do in this case, we actually compare this to the distance, and the result will be yes, no. They're related or they're not related. But in practice, when this computation is used, there's an additional complication. And basically, what it is that when they take a picture of the iris, right, I can tilt my head a little bit. And so it means that when I get one iris and another, I can't necessarily compare them directly. And so for that reason, they apply a rotation a couple of times to one of the biometrics. Okay? And so in this case, you want to compensate for small basically differences in the head in head tilt. And so for that reason, you choose a particular small constant, right? We say we're going to tilt it to the left 5 times using some unit, and then to the right. And so the computation becomes as follows. So in this case, I'll use left shift and right shift. This is a circular shift, and I used I times. So we take the one biometric is unmodified. The second one is shifted to the left a few times, right? Starting from 1 to C, and then it's also gets shifted to the right. And we want to make sure that we're finding the best match, okay? The best alignment, and based on that, we'll compare it to the threshold, okay?
Does the mask also get shifted? Or?
Yes, they're shifted together. consistently.
Does the iris not rotate without the head rotating, given how the eye can move with the...
No. This is how it's extracted. Basically, they take a picture of your eye, then cut the part that corresponds to your iris and unwind it like this, right? So it becomes a rectangle that represents your iris, basically. Okay. All right. So let's look at secure execution of this operation, right? We want to compare it to iris strengths. And so what I'll be talking on right now is, two-party computation. In general, this part of it is going to proceed on encrypted data, and we're going to use homomorphic encryption. And intuitively, the distance itself will be computed using homomorphic encryption, where encrypted data is transmitted to one party, and the second party will compute the distance, and then they will engage in the computation to compare it to the threshold, okay, together. So we'll say if we want to use encryption, we know that the values that we can encrypt have to be integers, right? But we said that basically the distance that we obtain is value between 0 and 1. How we should be able to, how can we handle this? And so the answer to this particular question is pretty simple. So we will quantize the possibilities. We know that there are certain values for the distances that we compute. We divide for the other, and we'll just scale everything up, right? Say we will allocate a certain number of bits to represent, to mean basically some granularity to go from 0 to 1, and it will just represent our basically all of the computation will be lifted up by a certain number of bits, and the threshold is going to be an integer value in this case. Notice that there is a division. In general, division is very difficult. Well, not necessarily difficult, but it's expensive if we want to implement it directly. But fortunately, in this case, we can get rid of the division and not use it at all. Okay, so we restructure the computation in such a way that we don't have to do division at all. And so the way it happens, actually, what we're going to do, if you notice, this is the distance, how it's computed, and then this value gets compared to a threshold. Okay, so what we're going to do instead, we will take the dividend here and compare it to the threshold multiplied to the divisor. Okay, we'll just move it up right there, and we can compare. But this is actually not everything, right? If you look at this computation, we have this distance is computed multiple times over different versions of the same biometric, and then compare it to the threshold, and you actually take the minimum. You want to know if the minimum is below the threshold. But now the divisor here is different from divisor here, and basically all of them are different. You can't necessarily just take it one and take it out and multiply it to this threshold so that all of them are going to be correct. Okay, but fortunately we still can not use the division. We can use this restructuring, but we are not going to do the minimum computation anymore. What we do instead, we replace this minimum with a Boolean OR. Okay, so the idea in this case is that we take the dividend of this distance and compare it to the threshold times the divisor. Then we do OR of this, the same thing, OR of this comparison, this and this. Okay, so the idea here will be if at least one of them is 1, the result is 1. This means that if at least one distance was below the threshold, the result will be yes. And actually it will correspond to exactly the same computation. Because minimum here in this case means that we'll find the smallest, and we know that at least one will match the basically computation that we're looking at, right? Will be below the threshold. So basically what we get is, after this transformation, what we're going to get is this formula. Okay, I would like to rewrite the computation that we had. So this d of x and I is going to be the dividend of the distance and m of x and y is the divisor of the distance of the exact same computation that I just presented. So now we will compare this dividend to the threshold times the divisor, or do the same thing over multiple shifts of the same biometric. Okay, so the computation doesn't change. The result is going to be exactly the same, but now we don't have to do division. Okay, and so when we also implement XOR, which is used throughout the entire computation, we're going to use arithmetic operations, right? So if you have bit xi and yi, and there are two different ways to write it using arithmetic operations, and we're actually going to use both of them throughout. For different computation, well, one would be better or the other. Okay. So next, what I would like to look at is actually the protocol itself, the interaction between Alice and Bob when they engage in a two-party comparison. Okay. So if we look here, first, Alice has a database, Bob has a biometric, and I'd like to compare the biometric to every entry in the database. So Bob will create a public key pair, public and private key pair for a homomorphic encryption scheme, and he'll give the public key to Alice. Okay, so he knows the secret key, and then Bob has this biometric X and the mask that corresponds to it. And so he's going to encode it, he's going to encrypt it and send it to Alice, but it's important to make sure that the encryption allows Alice to compute the distance. Okay, you can't just encrypt one bit at a time, and because otherwise it's not going to go through, because the computation is actually not as simple as just the inner product or Hamming distance. So what Bob sends instead, he encrypts each bit of the biometric multiplied with the corresponding mask bit. And you do the same thing, only where you have a complement of the biometric bit multiplied by the mask bit. Okay, so once Alice gets this information, she actually will be able to compute both the dividend and divisor of each distance. But what she'll need to first compute to be able to do so, she'll take these two encryptions, multiply them together, and if you look, this value xi and 1 minus xi will cancel out, and what she's going to obtain is just encryption of the mask bit of a single bit.
There's dot product of xi and xi, right? There's dot product.
No, this is one encryption. This is another.
But you're doing dot product, right?
No, right now, this is a bit and this is a bit.
Oh, bit, right?
Right. So when I say xi,
and
it means a particular bit of the string. Okay. So basically, there's a binary string, and they'll send an encryption of one bit at a time. Okay. So this is a bit, and this is a bit, and they compute a bit here as well. Okay. So basically now Alice, for each bit of the original biometric, Alice has 3 ciphertexts. This is the first, this is the second, and this is the third. And she'll want to compute basically the encrypted dividend that we have here, and this is the divisor. Okay, so let me just expand this and see how they would compute this. Okay, so for each biometric in the database, Alice will take it and produce multiple versions. She'll rotate it multiple times, okay, according to this constant that they have, C. So this is 2C plus 1 rotations of this biometric. So to compute this, basically, the first part of the distance, basically what they need to do is, this is XOR of XI and YI, and this J means that it's a shifted version. It's circular shift, you can always produce it, right? And so this part is the XOR, and then you multiply it by the first mask bit from the first iris code, and this is the mask bit from the second iris code. And so if you look at this, basically she'll take the first ciphertext that she got from Bob and raise it into basically the values that she has. Okay, so this is encryption of a bit. This is also a bit, and I will multiply to the second one, raised also in certain power that depends on the values that she knows. Okay, so if you look at this AI1 encodes basically the bit of the first biometric and the mask bit together, right? And this is what Alice adds to it by raising it to this power. And the second component here has the complement of the iris code bit and the corresponding mask bit, and this is what Alice adds to it. Okay, so as a result, you will see that if you take this, this mask bits, you separate them from the rest of the computation, put outside of the brackets, you'll get exactly the same computation. Okay, so this computes XOR of 2 bits multiplied by the mask bits. And what we need to do to create the Hamming distance, well, the distance across all of the bits, is to add them together. So this is for 1 bit, and you multiply the corresponding ciphertext m times, and you get the overall, basically, encryption of the distance. Then the divisor is actually easier, because what we have here, we have the first mask and the second one, and we need to compute their intersection, or the number of bits that are set to 1 in both of them simultaneously, and multiplied by the threshold. So in this case, Alice will take the third ciphertext from Bob that actually she computed, just encodes a bit of the mask bit, raise it to this power, and what you're going to get is desired computation for a single bit, and once again you multiply them together to get their sum, and raise it to the power of t, which is the threshold, to get the desired computation. Okay? So this is all can be done by Alice without any interaction, and as a result we have 2 parts that now we need to compare. This was the dividend of the distance, and this is divisor multiplied by the threshold. And so the only operation that remains right now is the comparisons and the OR of all different shifts. Okay? And one thing before I go to the next slide I would like to mention is that all of those operations are in bits. Okay, the ciphertext is a bit. This value, that the power is either 0 or 1. So they're not regular exponentiations. They're actually, well, basically, if it's 0, it means that you don't even need to use it, right? If it's 1, you take it unmodified. Okay, so this is going to be later very fast. Okay, so to finish this, the last step, as I said, is to do secure comparisons. You have to see plus 1 of those, and then you need to do the OR of the resultant bits. And so the most efficient way to do comparison with 2 parties is to actually use, Garble circuit evaluation.
I mean, without the randomization order added to it, isn't there a, because I know mask is just 0 or 1. Right, Bob could. Right.
Yeah,
you said the encryption of mask, right? So I could just check whether encryption of 0 and encryption of 1 and figure out what mask is, because you've been adding in randomness.
So are you talking about the result? This one?
No, if you go one step before, I mean, just the thing which Alice, the next.
So
you
this
will
one?
add R to it, you're saying. No, the 2 information, AI3. What is AI3?
So AA, this is a product of 2 ciphertexts.
So this one I'm saying, because you didn't add any randomness to it, MXI is just 0 or a 1, right?
Right.
It's a bit, right?
Right.
So could we just check with encryption of 0 or encryption of 1 and figure out what it is, because you didn't.
Those are randomized encryptions, right? The encryption itself is secure.
I see.
Right. Right. The encryption, just by looking at the ciphertext, you can't try all of the possibilities.
But to do the operation there, do I need the...
So later on, if you look at once we decrypt, we're actually going to randomize it, okay, before we proceed to the decryption. So at this point, the last point, because now they're going to decrypt and use a garbled circuit evaluation for the comparison. So to be able to actually decrypt without either party learning what they've computed, they're going to split it, okay? And so in this case, Alice will just add a random number to the computation, right? And she'll keep this random number as the her share. And what Bob will obtain basically is an encryption of the actual distance that is blinded, but hidden by the random number. And when he gets this value, he doesn't know what the distance was. Okay. And later on, I will actually. This will actually, how it's done depends on the encryption also. I'll mention this later on, okay? So this was the basic idea behind the protocol, but once we implement it or want to use it in practice, there's a lot of different optimizations that you can do. And the first one that actually made a huge difference for us was the choice of the encryption scheme. Okay, when I say editably homomorphic encryption scheme, everybody, people actually often use payload encryption, which is, very popular, right? But it turns out that there is a newer encryption scheme due Damgaard, Geisler, and Kreugaard, which was designed for comparisons. Okay, so basically the only way how it was used to encrypt one bit. And the plain text space is very small and actually variable. You can set it to anything you want, and it was very helpful for us in this case. It actually sped up all of the public key operations by about a factor of 10. Okay, so you get an order of magnitude improvement compared to what you had previously. And then when I'm computing those. When I'm doing those operations, there's a lot of it that can be pre-computed. Mm-hmm.
The reason you get the gain is because it's specialized for a small text.
It's small plain text, right? They used it for 1 bit, but you can say I need 20 bits. Okay, so it's both the plain texts are shorter and the operations are faster. And so basically in this case, when we say there's a lot of computation that can be done in advance before you know what your biometric would be. And in particular, the encryption uses randomization, right? There are normally modular exponentiations that you can do in advance by choosing random coins. And what's interesting in this case, we can even, Bob can even pre-compute the encrypted bits if you want it, or even send them. That there's optimization where you can just send something in advance, so later on the work for you is so little when actually the input becomes available. And what I mentioned previously is that if you go back to the computation where they were computing the product, right? So say this product combines m different ciphertexts, okay? But if we notice that this ciphertext was produced, taking some value that's already available, raising it to a certain power, which is a bit. If this bit is 0, right, means that I'll just ignore the ciphertext. It is not used here, okay? So basically, in my case, if certain bits here are 0, means that instead of doing m modular multiplications, I'm going to do 75% of the work, for instance. And if you look at this, those are products of 2 bits. If at least one of them is 0, it means that I can just discard this operation. I don't need to do that modular multiplication altogether. Okay, so you're doing a savings here, and there's an additional saving that I'm not going to go into details, where you can process multiple bits together. Okay, instead of doing 1 at a time, you can do 2 or 3 together at the cost of some one-time pre-processing that actually independent of the number of entries in the database. Okay, so basically this is primarily all that I want to talk about this type of computation, and I briefly mentioned the the implementation that we had, as I said, the choice of encryption made a huge difference. And another advantage that you get by using encryption that has small plain text size is then when you decrypt, right, the values are going to wrap around modular a small number, okay? Now, normally when you actually would like to decrypt and feed something into a circuit, you need statistical security, okay? You need values that's significantly bigger than my value that I'm trying to hide. The fact that I'm now using small plain text that's going to wrap around, I'm actually protecting that better. I don't need the statistical security parameter, and I can use values that are significantly smaller, and my circuit is going to be faster because the inputs now are short. Okay, so this is an additional advantage. So,
you set the size of plain text during the key generation or something?
Yes, yes. And basically, the decryption operation is linear in the size of your plain text because you're computing discrete log. But by choosing the plain text space accordingly, if it's smooth group, you can do this very efficiently. Okay, you have control.
You can also, let's say, use like code bus recovery, which is bitwise, and then like encrypt bit by bit. That would be less efficient, right? Or let's say use LGML or maybe index exponent, and then do bitwise. Those would be less efficient,
right? In our case, LGML basically is going to be slower, right? Because you have to try them all. In our case, the values that we're computing, maybe 20 bits, right? You have to brute force through the entire space. In our case, you don't need to. You do the number of module multiplications that says 20, right, to decrypt. Anyhow, it was tremendous difference in their performance.
Remind you, M is the number of bits in the iris, and what is C?
C is how many times we're shifting it left and right.
Oh, so five shifts.
Right, so overall we're doing 11 shifts. Well, 1 without shift, and 5 shifts to the left, 5 shifts to the right, so we get 11. So if you look at this, in the computation, we have the iris bits that are 2,000 bits. We're shifting them, or we're doing the computation 11 times. So it's about 22,000 ciphertexts, right, or operations that we need to do, and the performance is actually very fast, right? It's a fraction of a second. We have 0.2 seconds to process one basically biometric. And if actually the database that our biometric group at Notre Dame has is actually the images are pretty well aligned, especially if you take a picture of both eyes at the same time. They're going to be very well aligned, so you don't necessarily need to do any shifts. In this case, you can do something like 15 milliseconds per comparison.
Well, earlier you said that the iris was 250 bits. So
No. This is the amount of entropy that they have, but they can represent it using values that are that short. So the representation is redundant. Mm-hmm.
So you wouldn't do the OR, you just do the first one without shifting, and if it is 1, then you just not do the rest.
Right. So here you have to do 11 of them in parallel, but then you would use just 1. Mm-hmm.
Just to get a sense of performance, how many Y values would you expect to have?
Well, it depends on the size of the database, right? If it's, it could be 100, could be 1,000,000, depending, what you store there. Right? Large databases probably will be on the order of millions if you want to do this.
So this looks like you can do a public key operation in 10 microseconds. That's fast. I'm just dividing.
Right. So the part of it is that we're skipping some of them, right? We're throwing away some of them depending on the input, right? Because we know input is 0 means we don't have to do the operation. We can skip it. So you get savings this way.
But this time it needs the time to do the garbled circuit part too.
Right. But the garbled circuit is small because it's just simple comparison. You over 20-bit values. It's it's very fast. It's probably like 2 milliseconds. We actually have timing. So this work is going to appear in SORIX this year. So if you want to see more information, you're welcome to look at the experiments that we had and the exact timing. We were very detailed there. Okay, so let me look at the outsourcing. So outsourcing, when we say outsourcing, we now mean one party. There's only Alice, right? And Alice has a database the same way, and she has a particular biometric. She wants Iris want to know if it appears, and Alice is weak. She doesn't have the power to go through this large database, so she would like to outsource this computation to a more powerful server. Or in some cases, it's possible that basically the computation can be outsourced to multiple providers, in which case it could take the form of secure multi-party computation. And it would be faster, and it's going to be more powerful in terms of what kind of functionality you can compute. Okay? So basically, for one server solution, we're using a predicate encryption. And in this case, basically with predicate encryption, what you get is there are certain attributes that will associate with one biometric, and there will be predicate that will be associated with a different biometric. Okay? And so a ciphertext has attributes encoded in it, and when you have basically a key that represents a certain predicate, you'll apply to the ciphertext, and the decryption is successful if and only if the predicate evaluates to true on the attribute that's encoded in the ciphertext. Okay, so the most powerful type of the predicate encryption that we have is just the inner product. So it's not necessarily very flexible in terms of what we can do with this, but intuitively how we're going to do this, we'll store a encrypted database where each plain text corresponds to a particular biometric, and there are certain attributes that encoded in each ciphertext. And when new biometric comes in, Alice will create a certain key with the attributes, or with the predicate, right? And the server will apply this basically predicate to each of the ciphertexts that they have. And actually the server will learn which of the biometrics, if any, matched. Okay? So in this case, Alice gets just the answer of the form, the biometric number 253 matched. Right? The server will know if there was a match or not. In this way, Alice doesn't have to receive output that's proportional to the database size. Okay? So Alice will just get the indices for what biometric matched. So I'm not sure if I actually have time to go through everything. So this is yet a separate work that we've done, and this is, it's under submission, but you can look it up. I put it recently on ePrint, right, just last week. So if you want more details, you can look it up. But the idea behind this computation was that we couldn't do the division, right? And the trick that we had before is where you will, just take the divisor and multiply to the threshold would work, because in this case, the only way where you could do comparison is, say, is the distance between these two biometrics 1 or 2 or 3 or up to a certain threshold. But if you're comparing to a variable number that's not known in advance, you can't do this. Okay? So what we've done instead, we say we're going to use an approximation. There's no division. We're just going to drop the divisor altogether. But we did experiments on the Iris database using a more robust representation. Basically, instead of taking one sample, you sample the biometric several times and create one that corresponds to the majority. Okay? For each bit, you compute the majority, and it's actually, we've done some experiments, and it showed that it's pretty robust, different types of approximations that you might want to do on this type of data. Okay? So the idea was to encode this using inner product. And the inner product in this case supports evaluation of polynomials and testing whether a particular polynomial is equals to a certain value. You can do also ORs. So in our case, you can do all of the ORs. You can do comparison by basically trying a lot of different values. Okay, so this method is not efficient. It does not compute the distances exactly. It computes an approximation, but the approximation is good enough. The only problem is it's actually not going to be very practical because this computation tends to grow fast. Okay, so I'll probably skip the slides that describe how you would form the basically attributes and predicates themselves. This is how we've done. But the idea here would be that each attribute corresponds to a function of the biometrics. This is function of the first bit of the biometric stored in database, and then the second, and then you keep going until you represent all of them. Okay, and so for the predicate, you do the same or similar thing with the other biometric. Okay, and so the inner product will be tested for equality with a certain values. Okay, you test it with 1, 2, 3, etc. up to t-1. And for different shifts, you can do OR as well. And basically, you'll be able to obtain the answer. Is it within the threshold or it's not within the threshold? And then the server will learn this value and will inform Alice what biometrics matched. Okay, so I think I'm going to skip this. And then the second choice for outsourcing is to take the computation to multiple servers, right? And in this case, as I mentioned, it could take form of a secure multi-party computation. It could be much faster. Well, it will be much faster in our case. And it's obviously more powerful in terms of what you can do. And what was interesting in our case, we'll say we're going to use multi-party computation that use linear secret sharing scheme. And in this case, the computation will be structured in similar way to how I described for the two-party computation. But what's interesting is normally for techniques that are based on linear secret sharing, all of the linear transformation, linear combination of different shared values can be done locally with no interaction, right? You compute addition, multiplication by constant locally, but when you multiply by a shared value, then you need to engage in an interactive computation. This is what is the most expensive part, right? You count how many interactive computations you need to do. And what was interesting in our case is that the interaction is not linear in the size of the biometrics. Okay, you can basically do an inner product at the cost of one multiplication. And this is what is used heavily, this computation. Basically, what we're going to do, the inner product has cost of 1. Okay, and the value that we get, the result of inner product, when you actually do Hamming distance on the bits, the result is the number of bits that you need to represent. The result is logarithmic in the length of the biometrics. Okay, so when we're comparing them, the work is linear in log m, not m. And I found that this is actually significant, right? So you have those values that are thousands bits long, but when you actually all of that is processed locally on the shares, you pay the cost of 1 to compute basically their inner product, and then you compare this product to a different value, which will cost you number of interactions that are linear in the representation of the value. Okay, and because it uses standard techniques, you can also go to active adversaries by just using the standard, measures when the parties have to prove that they have actually behaved correctly at each step. Okay, so as I said, if you're interested more in this work, that there is ePrint. It's the paper is available on ePrint. And so the last thing that I would like to mention deals with verification of outsourced computation. Okay, So in this case, we assume the same scenario, that comparisons are outsourced to a third party, right? And the result comes back to you. And basically, the verification that we're concerned with is we're saying the adversary is not particularly malicious, but the adversary tries to save their computing power, right? We're giving them a large task, but it's possible that they're not interested in doing all of that much work. They'll just want to give something back to me and say, this is the answer, right? How do I know that the answer is correct? So what we're trying to protect against is so-called lazy adversaries that are not going to do all of the work. They'll skip some of it, and they want to give the answer back to us so that hopefully we wouldn't know that they didn't compute anything. Okay? Maybe they will just guess something at random. Maybe they will take one part of the computation, copy over, and give it to us as the correct result. And I would like to know whether this been, if the actual server did enough work to compute most of the results or not. And in particular, the guarantees that we would like to achieve is, can be something of the following, right? If the server performed, say, 95% of the computation or less, 50%, 20%, anything up to this value, we would like to be able to detect this cheating with a certain probability, such as 99%. Obviously, if the adversary didn't compute just 2%, this probability will go down, right? We are not going to guarantee the same result, but we say maybe 2% is not that significant. We can live with a small error, okay? So basically, up front, we have two parameters. The first one is assumption on how much work the server done, and the second one is with what probability we won't be able to tell.
95% or more, right?
If the server performs 95% work or less, so that 5% was not computed, and the server gives us something as, corresponding to those 5%. Okay, we would like to be able to tell with high probability that this took place. If they computed 99%, we probably might not be able to tell. But this depends on the guarantees that were given are set up front before we send the computation in. Okay. So basically, what we've done this for a slightly different setting, and in particular, so the previous scenario when I said that Alice has a database and would like to know if this biometric appears in a database. The previous solution was such that Alice would get only indices of the values that matched. Okay, if in this case, if you want to be able to verify the computation, you actually have to get something for each comparison. Okay, Alice will have to get a result of the first comparison, the second, the third, and there should be some sort of interaction or some sort of communication that will let her verify each result. Okay, so instead we'll proceed with a slightly different setting, and this is what is used at Notre Dame when I said that there is a massive computation that takes place and it gets placed on the cloud or a grid. And the idea in this case is, the computation is so-called Pairs Computation. When you have a database, right, and you put this database as rows of, your matrix and, as columns as well, and what you need to compute is the distance between each pair of those, okay? Basically, the idea is to find all of the distances between each element and all other elements, and then, perhaps given this information, you want to compute some statistics about the distribution of those distances, okay? You might actually want to separate distance of basically computation of distances between related biometrics and computation of distances of unrelated biometrics so that you have two different distributions, okay? So the idea in this case is the client has a database and actually can do work linear in database size, but to compute all pairs, it's quadratic, okay? And this is much bigger, so if the database size is 100,000, then obviously, n squared is going to be, billions, right? And so in this case, basically the verification could be also somehow linear in the database size. But when in our particular work, what we do was say we can basically, in this case, to compute statistics, we compile information. The server will compile information without losing any distribution information. Okay, basically what the server will give us is say, 250 values had distance 1, certain number of values or distances had this value. So basically you have you don't lose any information. You present complete information about the distribution, and the client can compute whatever statistics that it's willing to compute from that. Okay, so this is how the computation is given back to the client. Of course, the server doesn't know what it's computed. So just a little bit more on the ideas that we had. So the ideas are actually simple. The analysis is complicated. Okay, and so the idea is we have this data set, but we'll insert some of the fake elements that are inserted in random positions. And the server doesn't know where they are, so it doesn't matter how the server tries to cheat by copying something over or guessing at random. These values are unpredictable and unknown locations. And if we insert enough of them to meet our security guarantees, that with high probability the server will be caught. And another additional flavor of this computation in particular is that each biometric consists of a number of elements. Okay, it's not one single unit. There are multiple bits, or if you look at different type of biometric like faces, there'll be also multiple values in a 50-dimensional space that you have to combine together. For that reason, we also have to insert fake elements to make sure that the server just didn't compute the first 90% and stop there. Okay, we challenge the server sort of two different aspects. One on the fake items, and the second one is on fake elements within each item. And so in this case, basically, our analysis for just computing all pairs is independent of the distance. Works for all of them, but when you go to statistics, it actually depends on how the distance is computed, and we treated the Hamming distance, the Euclidean distance at center intersection. Okay, so let me see. This is probably everything. So if you're interested in this type of work, this is also going to appear in PSAT this year in October. But it's short paper. We have a full version, which is a technical report. If you're interested in it, you're welcome to look at it as well. Okay, so I'm going to conclude here, and hopefully I convinced you that computation of biometric data or outsourcing is something that we're interested in pursuing. See how we can do this more efficiently, and this is perhaps one of the directions that I would like to see. I would like to continue working on to see how we can do this faster, right? So this is actually feasible, and for me, if actually I would like to convince our biometric group, right, that this is okay to use, and the security techniques can enable them to use external computing power elsewhere. All right. Thank you for your attention.
On the previous slide, is that you insert some biometrics that you already know the answer for, or why can't you just go ahead and compute the answer for real ones?
Right. So basically, what we do, we insert fake ones that are pre-computed, right? They're known, and because the server doesn't see the data itself, we can reuse them over and over. Okay. So they could be the same, just inserted in different location each time. So that saves some computation. I mean, but a lot of it, all of it assumes that the server doesn't see the data.
So you randomize the encryption, so it's the plain text data that stays the same.
Right, so meaning whether this is encryption or secret sharing, you will need to make sure that they can't tell that's the same thing.